On a dark night, when you lift your head and look at the sky, you see the flawless stars shining in that endless darkness. But have you ever wondered how far you are actually looking? All those stars we can observe with the naked eye at night, even though they seem incredibly far away to us, are actually only a few hundred light years away when we think in astronomical scales. These distances, when the immense vastness of the universe is considered, are almost like nothing. That is why finding a trace that extends beyond our galaxy with the naked eye becomes quite a difficult task.
If we didn't have a powerful telescope that makes farther distances visible, we would probably think that the entire universe is only a few hundred light years in size. But right here, there is always an exception in the sky. Beyond planets, stars, black holes, and everything we know and can define, a completely different reality is waiting for us. Thanks to the billions of stars they contain, the central region of a galaxy can shine as brightly as 2 trillion suns. Just imagine the light of 2 trillion suns. However, the mind-boggling size of the universe and the incredible distances between us and these galaxies make most of these giant structures invisible to us. For this reason, even today, we can only attempt to illuminate the mysteries of these massive celestial islands with extremely advanced telescopes.
But among these billions of galaxies in the sky, there is one that does not hesitate to reveal itself to us. If you know well where to look in the sky, without the need for any telescope or binoculars, using only your eyes, you can see this galaxy. This galaxy we are talking about is located in the northern hemisphere sky in the Andromeda constellation, which shares the same name as the galaxy itself.
The name Andromeda, like other constellations in the sky, comes from Greek mythology. In mythology, Andromeda is a princess who is chained to a rock to be sacrificed to a sea monster sent to the land as punishment as a result of her mother Cassiopeia's arrogance. Finding the chained princess in the sky is actually quite an easy task. For this, first of all, it is necessary to find Cassiopeia, the mother of the chained princess mentioned in mythology, also known as the Queen constellation. The Queen constellation, in the northern direction of the sky, resembles a giant letter W. You can easily notice the total of 5 stars that form the main outline of this constellation. However, to reach Andromeda, we need to focus on the brightest of these stars, namely the star Shedar.
The direction that the star Shedar points to is always toward the Andromeda constellation. After finding the star Merak in this direction, in the region where the second and finally the third star are located, the Andromeda galaxy greets us. But be careful, the Andromeda galaxy appears faint or like a small cloud to the naked eye. Therefore, to be able to see the galaxy, you must be in a dark place far enough away from light pollution. The chained princess, or Andromeda, whatever we choose to call her, the most distinctive feature of this galaxy, unlike other galaxies, is undoubtedly that it can be seen with the naked eye. This situation makes the question, who first discovered Andromeda, meaningless. Because thousands of years ago, since there was no problem like light pollution, anyone who wanted to see it could look at the sky and spot Andromeda.
Humanity has always tried to understand what this mysterious smudge in the sky is. And once we began to understand the Andromeda galaxy, we had already set out on an irreversible journey. This is not only the story of Andromeda, but also the story of humanity discovering its place in the universe. When we look at the first efforts to record and describe Andromeda, we go back to the year 964 AD. At this date, the Persian astronomer Abd al-Rahman al-Sufi, in his book called Fixed Stars, cataloged stars and celestial objects. And in this very book, he described Andromeda as a blurry smudge or a small cloud. Since it would take a long time for equipment like telescopes, which would allow detailed examination of this object, to be invented, after Sufi's record, not much work was done on Andromeda until the 1600s. Andromeda, for centuries, remained a mysterious haze in the sky. In 1612, the German astronomer Simon Marius, using a telescope, became the first person to make detailed observations of Andromeda. In his observations, Marius noticed that the brightness of Andromeda increased toward the center. But at that time, we were not even aware that our own galaxy was a galaxy. In fact, there was not even a definition called galaxy.
At that time, we thought that our galaxy, the Milky Way, was a structure that contained all the stars and everything in the universe. In other words, the entire universe consisted of the Milky Way. This was not only because astronomy had not yet developed, but also partly due to a belief that had lasted for centuries that we should hold a privileged position within this universe. So much so that Marius, as a result of his observations, thought that Andromeda, both because of its brightness increasing toward the center and because of the area it covered in the sky, must be a nebula that was quite close to us. Indeed, Andromeda covers a large area in the sky. Like Marius, we too can, with the naked eye, notice the brightness at the center of Andromeda. However, if we could see Andromeda in its entirety bright enough, we would realize that it appears in the sky much larger than the full moon. That is why Marius's thinking that Andromeda was close to us was quite natural. In the century after Marius's observations, in 1764, the French astronomer Charles Messier would notice that, apart from Andromeda, there were dozens of different hazy objects in the sky. At that time, Messier was observing comets, and he realized that these objects could not be comets because they did not move at all in the sky. For this reason, although he did not know that these objects were galaxies, he decided to prepare a list to avoid confusing them with comets, and compiled the famous Messier catalog, which is still frequently used today. In this catalog, Andromeda found its place with the number Messier 31.
Towards the end of the same century, the German astronomer William Herschel took the stage and made an interesting observation. He was a telescope maker, and in 1789, he built a telescope with a mirror diameter of 120 centimeters. This telescope was the largest telescope ever built up to that time. Herschel, who began observations with his telescope, noticed that there was a faint red region in the central area of Andromeda. Based on the red color and brightness there, Herschel mistakenly thought that Andromeda was the nearest nebula to us. According to Herschel, Andromeda must have been only about 18,000 light-years away from us. In 1845, William Parsons discovered that some nebulas, including Andromeda, had spiral arms, and for the first time he depicted the spiral arms of Andromeda in a way consistent with his observations. With Parsons, astronomy had gained a new concept, spiral nebula. According to astronomers, these objects were nebulas within our galaxy that had their own spiral structures. In fact, the word nebula comes from Latin, meaning mist. So when they called Andromeda a spiral nebula, they were not even talking about nebulas in the sense we understand today. But the strange thing is that even before the observations of Herschel, Messier, or Parsons, in 1755, there was a famous name who had made a much greater claim than all these nebula ideas, Immanuel Kant. Kant thought that these hazy objects could be other structures located outside our galaxy. For this reason, he used the term island universes for these objects for the first time.
This idea of island universes ignited the spark of a very big debate that would last for many years.
because if these objects were other universes, their distances would have to be far, far greater than what the astronomers of the time, such as Herschel, had calculated. Therefore, even though this crazy idea was not accepted by many astronomers, astronomers were divided into two groups. Some agreed with Kant, thinking that these objects were other galaxies within the universe, while a large portion believed that they were regions within our galaxy that led to the birth of stars. In 1885, a discovery was made that would allow Kant's ideas to be discussed observationally. In the Andromeda galaxy, a supernova explosion called SN 1885A became even brighter than Andromeda itself. However, at that time, the distinction between supernovas and novas was not yet known. According to Harlow Shapley, a nova could not be as bright as a galaxy. Therefore, Andromeda should not have been an object the size of a galaxy. This observation had led to the discussion of Kant's island universe idea. However, another astronomer named Heber Curtis was approaching this observation from a different point of view. Other novas observed until that time had been seen in completely different regions of the sky. But together with SN 1885A in the Andromeda galaxy, many other novas had also been observed. This situation, that is, the observation of many novas in a small part of the sky, required that Andromeda be much farther away than our galaxy. Because if Andromeda were a nebula very close to us, it would mean that there were many nova explosions in a very small area of the sky.
This debate between Heber Curtis and Harlow Shapley went down in history as the Great Debate, and it became one of the most important milestones in the history of astronomy. If Heber Curtis was right, the universe was much, much larger than we had thought until then. This would also show that we did not hold a privileged position in the universe as we had believed. If Curtis was right, we would have to accept that we were nothing more than a small speck of dust in the universe. There was no clear winner of the debate. Because we could not measure the distance of the Andromeda galaxy, the distances of nearby stars could be measured, but as the distance increased, making measurements with the parallax method became increasingly difficult. To measure the distances of galaxies, we needed a more modern and different method. A few years after the beginning of the Great Debate, which still had no winner, in 1923, Edwin Hubble, with the 2.5-meter Hooker telescope at the Mount Wilson Observatory, was searching for a Cepheid star in the Andromeda galaxy. Of course, Hubble had an important purpose in searching for a special type of star in Andromeda. Cepheid variable stars are stars whose brightness changes over periods of 1 to 120 days. These stars, in fact, swell and contract again because they have reached the final stages of their lives. In other words, these stars are pulsating stars. Since this happens in a specific pattern, when viewed from Earth, we also see regular, or in other words, periodic changes in their brightness. Just like the regular flickers of a candle flame, the brightness of Cepheid variable stars also increases and decreases at regular intervals. This candle-like change in brightness is very important. For example, let us imagine a candle flame located at a random distance from us. We know the brightness of this candle flame relative to our position. We call this apparent brightness. However, determining the distance of this candle flame using only the apparent brightness is not possible. For this, we must know how bright the candle truly is, independent of distance. In other words, its intrinsic luminosity. When we can determine the intrinsic luminosity of the candle, since we already have the apparent brightness, with these two pieces of information, we can calculate how far away the candle is. Therefore, if we want to measure the distance of a star, we must know its true brightness. This is where Cepheid variable stars come into play, because in the years before the Great Debate, Henrietta Leavitt had discovered that there was a relationship between the pulsation periods and intrinsic brightness of these Cepheid variable stars.
This period luminosity relationship, also known as the Leavitt law, allowed us to determine the true brightness of a star. That is why Hubble, if he could find a Cepheid star in the Andromeda galaxy, in other words, a standard candle, would be able to calculate the distance of the galaxy. He made an exposure of exactly 45 minutes on a photographic plate coded H335H. After examining the photograph, he marked 3 stars here as novae with the letter N, meaning new, because these objects were not present in earlier photographic plates and they had newly appeared.
However, Hubble marked one of them with his red pen in large letters as VAR, because Hubble realized that this star, called M31V1, was a Cepheid variable due to the brightness changes it showed, unlike the others, and therefore it was the key to a great discovery. If he could determine the period and the average apparent brightness of the Cepheid star he found here, he could also calculate the distance to the Andromeda galaxy, and by doing so, he could put an end to the long-standing great debate and solve the mystery of this hazy cloud that had been seen in the sky for centuries. As his observations continued, by the end of 1924, Hubble discovered 36 more different variable stars in Andromeda. 12 of them had the characteristics of Cepheid stars. Using the observations he made in 1929 and all this information, Hubble determined that the Andromeda galaxy was about 1 million light-years away from us. Of course, today, with observations made using much more advanced telescopes and more precise calculations, we know that the Andromeda galaxy is 2.5 million light-years away. So Hubble had actually found the distance to the Andromeda galaxy to be closer than it really was. But even so, 1 million light-years was enough to say that Andromeda was a separate, entirely different galaxy.
Andromeda really was another galaxy. All of a sudden, we had begun to grasp that the universe was a much bigger place. With this discovery, the winner of the great debate had been Heber Curtis. At the same time, we understood that Immanuel Kant, who had proposed the idea of island universes, had actually been right from the very beginning. It was as if we were looking at another universe in the sky. The Andromeda galaxy holds the title of being one of the most studied and most photographed celestial objects up to this time. Since the invention of the telescope, both amateur and professional ground-based and space telescopes have photographed this galaxy hundreds of thousands of times. So now we have more information about Andromeda than ever before. In fact, the foundation of all the information we have obtained about Andromeda so far depends on how well we have been able to photograph it. When it comes to photographing celestial objects, we never talk about instant snapshots, because celestial objects appear much fainter in the sky than what our eyes can see. Even with telescopes, the instantaneous image of a galaxy is quite lacking in detail and faint. That is why, in order to reveal all the details of an object in the sky, we need to collect its light for as long as possible. This is what we call exposure. Therefore, the longer we expose a faint object, the more light we collect, and the greater our chance of revealing the mysteries of that object, which normally appears faint to us.
Andromeda is also one of the most suitable targets for exposure, both because of the area it covers in the sky and its brightness. This Andromeda photograph, which looks as if it was obtained by a space telescope, was actually taken especially for this video by Ogetai Kayali. Not refusing us and using his telescope in Texas, Ogetai Kayali made a total of 11 hours and 45 minutes of exposure to obtain this photograph. In the resulting image, we can observe the brightness in the galaxy's core together with Andromeda's spiral arms. This curved structure in the spiral arms is probably the result of gravitational interactions Andromeda has carried out with the dwarf galaxies around it. In the photograph near Andromeda, nebula-like structures that are far too bright to be stars should catch our attention. These are Messier 110 and Messier 32, the largest satellite galaxies of Andromeda. If we look carefully, we can also see many galaxies in the background of the photograph. However, these are galaxies much farther away than Andromeda. All these details are a magnificent example of how much detail exposure can provide today, together with proper astrophotography techniques. These gases and dust responsible for that hazy appearance of the Andromeda galaxy in the sky, although they look pleasing to the eye, can sometimes also prevent us from obtaining accurate data about the brightness of the stars in the galaxy.
If we want to know the Andromeda galaxy better, we must examine it not only in visible light, but also in different wavelengths of light, such as infrared. This is where space telescopes actually come into play. For example, this is a composite infrared photograph of the Andromeda galaxy taken by the Spitzer Space Telescope. We call it composite because the Andromeda galaxy is very large, so Spitzer made 3,000 separate exposures in order to obtain these photographs. The main purpose of this study was to measure the total infrared brightness of the Andromeda galaxy, because the amount of infrared light coming from the stars in the galaxy is directly related to the masses of those stars. That is why Spitzer, by taking these photographs, also revealed the mass of the Andromeda galaxy. According to this, the mass of the stars in the Andromeda galaxy is 110 billion times the mass of the Sun. This value also gives us the chance to make accurate estimates about the number of stars in the galaxy. According to these values, the Andromeda galaxy should host approximately 1 trillion stars. For comparison, for example, the number of stars in our galaxy, the Milky Way, is roughly around 200 billion. The width of Andromeda from one end to the other is about 260,000 light-years. This means that a beam of light leaving the starting point of Andromeda would have to travel for 260,000 years to reach the other end of the galaxy. Again, if we compare, the size of our galaxy is about 100,000 light-years. So we're talking about a galaxy much larger and much richer than the Milky Way.
Despite all these differences, the Andromeda galaxy is a barred spiral galaxy just like the Milky Way. That is, the stars at the center of Andromeda form a bar-like structure, and the spiral arms spread out from here. Because the appearance of Andromeda is quite inclined from our point of view, we cannot easily distinguish this bar structure at the center in photographs. In other words, we cannot look at Andromeda directly from above. However, when the motions of the gases and stars here are examined, it becomes clear that the center of the galaxy must have a barred structure. This bright center of the galaxy is also a sign of a supermassive black hole. The mass of the black hole here is about 140 million times the mass of the Sun. Despite this mass, this black hole is surprisingly one of the least active supermassive black holes in galaxy centers. We can say this thanks to the relatively low amount of radiation emitted by this black hole. Because the gas and dust accumulating in the accretion disk around a supermassive black hole heat up before falling into the black hole, and this causes a significant amount of radiation to be emitted from the black hole. Therefore, how active the supermassive black holes at galaxy centers are depends on how the matter falling into the black hole behaves. In other words, how fast the black hole consumes the matter around it.
The low level of radiation at the center of Andromeda shows us that this black hole consumes the matter around it at a small but steady rate. In this photograph taken by the Spitzer Space Telescope, by focusing on the center of Andromeda, we can see how the dust around the black hole moves. In astronomy, thanks to filters that allow different wavelengths of light to pass, we can see gases, dust, and stars separately in photographs. For example, when we observe the Andromeda galaxy only in the band that reveals dust, we see the literal skeleton of Andromeda. Therefore, this photograph also reveals how the dust in Andromeda moves not only near the supermassive black hole, but throughout the entire galaxy. In the Andromeda galaxy, we can see that one spiral arm is dominant and that it also splits into two parts on the right side of the photograph. This situation may be evidence of the gravitational interactions that Andromeda has undergone. Of course, a large galaxy like Andromeda cannot be alone in its region. Messier 110, the largest satellite galaxy of Andromeda, is bright enough to be seen even with a small telescope. We had also encountered Messier 110 in the photograph of the Andromeda galaxy taken by Ogetai Kayali.
Although from a distance it looks like a small copy of Andromeda, when we get closer to this galaxy, we see that it does not have spiral arms like those in Andromeda. Because Messier 110 is not a spiral, but an elliptical dwarf galaxy. Since elliptical galaxies do not have spiral arms or star-forming regions, such galaxies are often called dead galaxies. At the same time, the stars in elliptical galaxies are older compared to the stars in other galaxies. This small elliptical galaxy hosts about 10 billion stars and also 8 globular star clusters detected so far. When we look at photographs of the Andromeda galaxy, apart from Messier 110, another distinct brightness draws our attention. This is Messier 32, another large and bright satellite galaxy of Andromeda after Messier 110. This satellite galaxy is also a dwarf elliptical galaxy, and like other elliptical galaxies, it mostly consists of red and old stars. Since it contains almost no gas and dust, it is not possible to talk about star formation in this galaxy as in the spiral arms of Andromeda. However, this satellite galaxy also hosts a supermassive black hole with a mass equal to 5 million solar masses. We know this from the radio and X-rays emitted from the center of the galaxy, along with the gases concentrated there.
Most of Andromeda's satellite galaxies are within a region of about 1 million light-years. But the satellite galaxies Messier 32 and Messier 110 are quite close to Andromeda. For example, the Andromeda galaxy was 2,537,000 light-years away from us. The Messier 110 galaxy is 2,674,000 light-years away from us. So there is only a distance of 100,000 light-years between them. Even from a distance of 2.5 million light-years, the Andromeda galaxy covers an area in our sky larger than the full moon. So if we imagine that we are on a planet somewhere in the Messier 110 galaxy, what would the sky look like? Even if it may not be exactly the same as this view, thanks to the space telescopes we have today, we can obtain images that take us on a journey inside Andromeda without needing to travel to the galaxy's satellites. This is the largest and sharpest photograph of the Andromeda galaxy ever taken by the Hubble Space Telescope. The entire photograph consists of 1.5 billion pixels. So if we wanted to see this photograph in full quality, we would need to place more than 600 HD television screens side by side. In this photograph by Hubble, we are looking at hundreds of millions of stars within a 40,000 light-year region of the galaxy. Along with these stars, when we look at some parts of the photograph, it is also possible to encounter star clusters. There are about 460 globular star clusters discovered in the Andromeda galaxy so far.
Along with its mass, the most remarkable of these is the Mael 2 globular star cluster. This cluster has a higher brightness than all the other globular star clusters we know in the local group, where our own galaxy, the Milky Way, is also located. This cluster alone contains several million stars, and it is about twice as bright as Omega Centauri, the brightest globular star cluster we know in our own galaxy. These values are much higher than what would be expected for an ordinary star cluster. This suggests that Mael 2, also known as the G1 globular star cluster, is the remaining core of a dwarf galaxy that was consumed by Andromeda in the past. Unlike the Milky Way galaxy, these globular star clusters in the Andromeda galaxy have a much wider age range. While some globular star clusters are as old as the galaxy itself,
In this galaxy, we also encounter clusters that are only a few million years old. As we wander through the Andromeda Galaxy with the star clusters, star-forming regions, and even black holes we encounter in every corner, we truly begin to feel as if we are looking at a completely different island universe, just as Immanuel Kant once said. This inevitably brings the following question to mind. Are there also other planets orbiting the stars there?
The answer to this question is yes on paper, because according to the dynamics of star and planet formation, almost every star in any active galaxy should have at least one planet around it. Of course, in order to talk about the possibility of life on these planets, we need to have information about many parameters, such as what type of star the planet orbits and in what orbital period. So even though we know that exoplanets should theoretically exist in the Andromeda Galaxy, we want to see them, to observe them. But directly discovering an exoplanet around a star in a small corner of another galaxy that is millions of light years away from us is truly a great challenge with today's astronomy, because none of the telescopes we have, including the James Webb Space Telescope, have such high resolving power. However, in the universe, massive objects like galaxies or star clusters can act as natural telescopes that cause light to diffract. So, for example, the light of a planet may be bent during its journey to Earth because of a massive object. We call this the effect of gravitational lensing. This makes the light of some objects visible to us, even though they are at distances too far for our telescopes to resolve under normal conditions.
In 2009, astronomers detected signs of the existence of an exoplanet in the Andromeda Galaxy using the gravitational lensing method. The existence of this exoplanet, named PA99N2, has not been confirmed. However, PA99 still holds the distinction of being the first exoplanet whose traces were detected in another galaxy. In other words, we are talking about an extragalactic exoplanet. However, the planets in the Andromeda Galaxy do not always have to stay with their stars. Like the dozens we have detected in our own galaxy, there must also be many rogue planets in the Andromeda Galaxy that were ejected from their star systems and left alone in the darkness of space. Talking about the possibility of life on any of these exoplanets would be nothing more than speculation because we have almost no data about it. But when we consider the size of Andromeda, its types of stars, and the richness it contains in terms of star-forming regions, it is also a fact how exciting the possibilities sound. Andromeda, which resembles an entirely different universe in the sky, may seem like an unreachable place with its distance of 2.5 million light-years. However, everything in the universe is constantly in motion, and of course, Andromeda is as well. According to the Doppler effect, as an object moves away from us, the frequency of the light coming from it decreases, and this causes the object's light to shift toward red. In the opposite way, since the frequency of the light coming from an approaching object increases, the light of that object shifts toward blue. The fact that galaxies in the universe show redshift indicates that galaxies are moving away from one another.
However, among all these galaxies that show redshift, Andromeda shows the opposite, namely a blue shift effect. In other words, Andromeda is not moving away from us like other distant galaxies, it is moving toward us. But until 2021, we did not know exactly when and at what rate Andromeda would approach us. With the help of the Hubble Space Telescope between 2002 and 2010, over a full period of 8 years, the motions of stars in the Andromeda Galaxy were studied relative to the background galaxies behind Andromeda. When the average motion of thousands of stars was calculated, it was discovered that Andromeda was moving across the sky at a rate of less than 0.1 milliarcseconds. In other words, Andromeda was indeed approaching our galaxy at a speed of about 110 kilometers per second. In fact, this is not a surprising or unusual discovery, because the merging of galaxies within galaxy groups is a relatively common phenomenon in the universe. Even the current morphology of Andromeda itself was shaped by mergers with dwarf galaxies billions of years ago. We can see the traces of these mergers in Andromeda's spiral arms.
Andromeda is indeed approaching us. However, we also know that this approach will take place over time spans far longer than a human lifetime. If we imagine looking from Earth in 2 billion years at this speed, the disk of the Andromeda galaxy will have grown noticeably larger in the sky. In 4 billion years, when we look at the sky, we would witness Andromeda covering the entire field of view in the sky. During this time, we could see the new star-forming regions created by the merger of the two galaxies shining brightly in the sky. For several 100 million more years, this merger would continue, causing the arms of both galaxies to appear asymmetric due to gravitational effects. In the 5th billion year, finally, the cores of the Andromeda and Milky Way galaxies would also be seen as bright clusters. When a total period of 7 billion years is completed, these galactic cores would have merged as well and formed an entirely new galaxy. However, since the spiral arms of the galaxies would have dispersed and the rich star-forming regions would have been consumed, this newly formed galaxy would be an elliptical galaxy. Even though we know this scenario will occur in 7 billion years, we will never be able to observe it the way we imagine here. By that time, our sun may have long since completed its life and swept away the entire solar system. Good night.